last class we have seen a number of 3 address code instructions which are there in 3 address coding strategy, and the last one that we are looking into are the procedure call and return. So, almost all the programming languages they have got some sort of procedure facility. So, if we get rid of that in intermediate language then there will be problem in the translation process. So, what this intermediate code designing technique assumes is that there is a very primitive type of parameter passing strategy and very primitive type of function call or procedure call that is supported, and similarly there is a strategy for returning from the procedure. So, to call a procedure with a p with the parameters x 1, x 2 up to x n. So, it will be converted into a block of parameter statement param x 1, param x 2 up to param x n. So, you see that we have not included the statements like say param and a number of parameters x 1, x 2 etcetera. So, in that case the difficulty is that there is no limit on the number of parameters that you are allowed to have in this statement. So, naturally you cannot code it in 3 address coding strategy. So, to make it very simple, so it has been converted into if there are n parameters, then it will be converted into n parameter statements, parameter x 1 to parameter x n. And then for processing for a procedure call, so it is done as enter f. So, enter f at this point several actions may be necessary depending upon the language for which we are generating the code and the target machine. So, it for example, it may require that these local variables they be assigned space. Okay. So, that is all those translations will be done at the enter f point. So, at a high level we just noted that it is calling the procedure f. So, it is enter f, and similarly at the time of returning certain actions are necessary to clean up the thing, like clean up the space. So, that is leave f. So, it will be doing some cleanup actions like say the space that was allocated to local variables. So, they should be given back. Similarly, there may be some dynamic variables created in the body of the procedure. So, after the procedure is over, those dynamic variables they will not have any meaning. So, they have to be disposed of. So, etcetera. So, that way there can be a leave statement at the end. So, this encapsulates all possible actions that may be needed for the cleanup procedure. Now, apart from that we have got the return statement to return from a procedure. So, in the first version of return, so there is no return value. So, it is basically the void type of functions that you have in C. So, if you want to come back from that procedure or function, so it may be a return. So, if there is a return value, then you can use this return x. So, that will be at the procedure you can have at the function end. So, you can convert it into return x and retrieve x. So, this save return value in x. So, this will be return value will be saved in the variable x. So, that way it will be converted. Like if I have got some say function say f 1 being called with some parameter a 1 a 2. So, at the time of call, so I should have these 3 address statements param a 1, then param a 2 like that, and then I should have enter f 1. Okay. Then at the body of when I am translating the f 1 part, I should have this local setup part. So, this is the local part. So, this enter f 1. So, the local part may be there. So, they will be created. So, at the end, so I can have this return or return x etcetera, and then this leave f will be coming at the bottom. So, leave f 1 will come at the bottom. So, that will be leaving the thing, and this return statement should come before that. Okay. And this in the main program. So, I can have this retrieve thing, like it may be that I have got a call like x equal to f 1 something. So, retrieve the return value into some temporary variable t 1, and then I can have x equal to t 1. So, this may be the final code that is generated, the 3 address code that is generated. So, there may be some variant of this, but this is one possible strategy by which we can do this translation. So, there may be some other statements like they come under the broad heading of miscellaneous statements. more statements may be needed depending upon the source language. So, the some source language it has got some special type of instructions which are not generally present in other programming languages, like say in C programming language we have got this next statement, break statement, like that. So, which may not be present in some other language. So, so they come under this broad heading. So, how do you realize a continue statement that you have in say C language, how to convert it into intermediary code. So, that may be a issue, that may be an issue, and that can be done by means of some go to statements. So, as you will see later. And one such statement is to define jump target. So, that is label L. So, it is like this, for jumping to a procedure we said that it is like go to L, okay. And then what is this L? So, somehow if this L is a procedure, okay. So, maybe I have in the main in the source language program I have got a call for a procedure. So, I have got x equal to f1 something, okay. Then there the go to L is there. So, it is expected that L I should start the procedure f1, here I should have the procedure f1. So, to do this thing, so this label has to be generated, but 3 address code label is not put like in this fashion. What we do is that we put another 3 address statement called label L, and then when this label L is encountered means at this point defines the beginning of the code. Wherever we say that it is a jump to the label L. So, the execution should come to this point. So, that is how these labels will be implemented, or labels will be meaningful in 3 address code. Now, how do you represent this 3 address instruction? So, 3 address instruction means that there are at most 3 addresses. So, every instruction is a quadruple. So, this is the first representation that we have. So, it is a quadruple representation. So, where each instruction has at most 4 fields. One is the operation that identifies the operation to be carried out. Like here is an example, like this is the, so here the operation is plus, here the operation is jump on greater or equal. So, like that operation it will identify the operation to be carried out up to 2 operands. So, so this is like this source 1, source 2. So, these are 2 source operand and this destination is the destination. Now, it may so happen that we directly mention the operand here, or we say that it is a pointer. So, there may be a bit here. So, that will identify whether this is a pointer or a normal variable, like say it is a constant or a pointer, like say x equal to y plus z. So, this is not a, so this is pointing to y. So, y is the symbol table for symbol table entry for that. So, whatever be the memory location allocated to y, the offset of that. So, that will come here. So, this bit will be 1 telling that it is a pointer. So, and the destination will also be there. So, this is a generic type of representation for 3 address code instructions. So, we have got an operation field, 2 opcode, 2 operand fields and 1 destination field. Now, so this is a typical example, like say if x plus 2 greater than 3 into y minus 1 plus 4, then z equal to 0. So, we are not talking about how are we going to do this translation. So, that will unfold as we proceed through this content of this particular chapter, but after everything has been done, the intermediary code will look something like this. So, this is your intermediate code, this is the intermediate code generated corresponding to the statement that we have at the beginning. So, you see there is a single line source, a single source language statement corresponding to that, so many 3 address code instructions have been generated. So, let us try to check it. So, first this x plus, so t1 equal to x plus 2. So, t1, t2, t3, t4. So, they are all temporary variables, and you will see that in 3 address code there will be a large number of temporaries created, because in 3 address code the individual operations they have got only 2 operands in them. So, we will be doing it like that, we will generate 2 address sub expressions or sub parts or sub instructions to store the result of those two address operations. Like in T1 we calculate x plus 2, in T2 we calculate y minus 1, T3 we calculate 3 into T2. So, ultimately T1 contains x plus 2 and T3 contains 3 into y minus 1, then T4 is T3 plus 4. So, this way we have generated the first. So, this part is evaluating this part is evaluating the expression that x plus 2 and so this T1 is evaluating x plus 2 and this T4 has got the value of this right hand side expression. Now, so if T1 is less or equal 4, so the our condition is T1 is greater than T4. So, in that case Z will be made equal to 0. So, the condition is generated in just the reverse of that fashion. So, if T1 is less or equal T4, go to L. So, go to L. So, this is a label and then we make Z equal to 0 and then the label L comes. Since we have got only a single statement in this code, so after label L there is nothing. So, if there was a statement here, if there was a statement like say y equal to p plus q, after doing this, then we will have this code for y equal to p plus q. So, another T5 equal to p plus q, then y equal to T5. So, that would have been done. But here it is so when it says go to L, label L, so it will search, it will come to this label L. So, that means my execution should start from this point if T1 is less or equal T4. So, this way 3 address codes will be generated. So, we will see how using different translation rules or syntax directed translation mechanism, how can we generate such 3 address code. Okay. So, first we consider a very simple type of statement, which is the assignment statement. So, we have to start with the grammar for the assignment statement. So, the grammar for the assignment statement is this one: S producing ID assigned as E, then E producing E plus E or E star E or minus E, that is this is unary minus within bracket E and ID. Now, so depending upon the assignment statement that is given to us, so it will be it will generate a parse tree, where the root of the parse tree will have this S and it will have like this ID assigned as E, and then E will further break down into a parse tree for the expression. Now, as far as reductions, so when this shift reduce parsers will work, so it will be trying to reduce the handles like this, and when it is doing this handle reduction or handle pruning, then it will be consulting the corresponding action part. So, this is so in this table we have written the semantic actions that will take place when the corresponding reductions are going to happen. So, suppose we have got this whole thing, this the entire expression has been calculated. So, at the last this particular reduction is being made. Okay. So, so in that at that point this code should be generated, so that this ID will be assigned the value of E. And how is it done? So, we assume that there are 2 attributes for the non-terminal E. One is called E dot place, that holds the name that will hold the value of E, and E dot code is the sequence of 3 address statements for corresponding to evaluation of E. So, if I tell you that E dot code has got so this E, it has got 2 portion, one is the place and another is the a pointer to code. So, if this is the code that is required for evaluating E, and E dot place is the name of the place or name of the temporary that finally holds the value of E. So, if the last assignment here, last computation here is say T5 equal to something, and that holds the value of this E dot place, then this the value of the expression E, then this E dot place will be equal to T5. Okay. Now, given this thing, so if I just look up by one more step this ID assigned as E, then what is the thing to be done for generating the code for S? So, in the code for S, I should have first the code for E, code for evaluating E. So, this should come as it is, and after that I have to do the assignment, that is this id dot place. So, id dot place holds the name of the id, like if actual statement may be a equal to b plus c. So, this id id dot place, so it will hold the value a. So, then this a equal to so this I will have this code followed by this extra code, that id dot place assigned as e dot place. I will have this extra code id dot place assigned as t5. So, this is the additional thing that I am going to have. So, this way we will try to write down the semantic actions that should take place when the corresponding reduction is being made. So, this reduction is done at the end. So, if this is the parse tree for E, you see that in a shift reduce parsing policy. So, this reduction will be done at the end of this all other reductions are done. So, by the time you are going to do the doing reduction at this point. So, this place and code, these two are already computed for E, and then we generate the extra code, that id dot place assigned as E dot place. So, this way I have got this two attribute E dot place and E dot code, that holds the name of the symbol that will hold the value of E, and the sequence of 3 address code 3 address statements that corresponding to the evaluation of E. Then for the non terminal S, we will assume that there is an attribute S dot code, just like E dot code holds the code for E, and then this S dot code holds the code for S. So, this is our S dot code. This is our S dot code. So, sequence of 3 address statements. So, that will be required for this statement to be executed. Then this attribute for the terminal symbol id. So, this is id dot place contains the name of the variable to be assigned. So, as I was telling that if it is a equal to b plus c, then id dot place is equal to a, and this is very simple to find out, because the lexical analyzer will get the value, will get the symbol as a. It will return id as a token, but you can always return as an attribute of this id the actual name of the symbol a. So, parser will know the name of the symbol by means of that YYLVAL type of attribute that you have. Then this from that you can while doing this reduction, we can take help of this and generate the complete tree for a complete code for S. So, this id dot place is there. Now, let us look into a very simple rule, that is the E producing id. So, what is to be done? So, E dot place should be equal to id dot place, because E dot place it holds the name that will hold the value of E, and that is the and id dot place holds the name of the id. So, naturally E dot place has to be assigned to id dot place, and nothing has to be done. E dot code is null, nothing has to be done at this point. Okay. Similarly, if you look into say this rule, say E producing within bracket E1, then E dot place equal to E1 dot place. So, because here whatever is the variable that holds the whatever be the symbol that holds the value of E, that is E1 dot place. So, that is that itself will hold the value of E. Okay. So, E dot place equal to E1 dot place, and then this E dot code is also equal to E1 dot code. So, that much is fine. Now, let us look into this rule, E producing unary minus E1. At this point, so I have to have something like this. So, so for generating the code of E, first I have to include the code for E1. So, I have to include the code for E1, followed by I have to generate a piece of code where this I need a new E dot place, because E dot place whatever temporaries have been used in the computation of E1. So, that cannot be used for the to hold the value of E, the E dot place. So, in this statement, so we have made E dot place equal to new temp, where new temp is a function that returns a unique new temporary variable. So, this is very simple, like if we have a counter, like how many temporaries have we generated so far in this in a compilation process. So, that counter may be incremented by 1, and after that the value may be attached to t to give a new next temporary variable. So, this way this E dot place equal to new temp. So, this new temp function will return a new temporary variable and that will be assigned to E dot place. So, as if that new temporary variable, so it will hold the value of this expression E. And what is the code for E? Code for E is the code for E1. So, this particular symbol, so this concatenates two 3 address code segments. So, this is a concatenation operator. So, if we think about the 3 address code statements as strings, then it is something like a string concatenation. Okay, definitely so, because ultimately what you have is nothing but is a text file only. The 3 address code that is generated is a text file, and so you can always take the individual lines of that text file as string. So, the E dot place assigned as unary minus U1 dot place. So, this particular code will be generated. So, this unary minus U1 dot place. So, this unary minus thing will be introduced, and U1 dot place was holding the value of U1 is the name of the variable that holds the value of U1. So, that will be negated by this unary minus symbol and that will be assigned to E dot place. Similarly, if we look into say this particular statement E producing U1 star E2, then also in the code for E I should have the code to evaluate E1, I should have the code to evaluate E2, and then I should generate an additional piece of code. So, that will multiply E1 dot place and E2 dot place. So, it is done in this fashion. So, E1 dot code concatenated with E2 dot code concatenated with this gen function. So, gen function it accepts a string and produces it as a 3 address quadruple. So, this is the whole string that is accepted that is taken as input by the gen function, and then it is generating this piece of code that E dot place. So, E dot place is already obtained, it is the corresponding temporary that we have got here. So, that temporary assigned as U1 dot place. So, a temporary variable which holds the U1's final value and then multiplied by E2 dot place. So, E2 dot place holds the final value of E2. So, that way they will be so this particular piece of code will be concatenated with the code for E1, code for E2 and then this one. And then similarly this E producing E1 plus E2. So, this is also similar as far as code generation is concerned. So, E dot place equal to new temp and then E dot code equal to E1 dot code concatenated with E2 dot code concatenated with generate E dot place assigned as E1 dot place plus E2 dot place. And then of course, I will need this particular statement E dot place equal to new temp to hold the to get a new temporary variable. So, this way for arithmetic assignment statement. So, we can draw the corresponding we can draw the corresponding parse tree and then follow these particular semantic actions. Okay, we can follow this, these are actually actions for the syntax directed translation mechanism. So, by which we can generate the corresponding code. So, here is an example like using that previous grammar. So, we have got an example string that is x produced. So, this x assigned as y plus z into minus of w plus v. So, this is if you look into the grammar. So, the root is s producing id assigned as e. So, this is the parse tree. So, s id assigned as e. So, id, this id is x. So, that will be known by the lexicon analyzer. So, lexicon analyzer will identify that id dot place as x, and then this e. So, this will be so this star will be generated. So, e star e. So, I am not going into ambiguity and all those things, and I assume that my parser is clever enough. So, it has been given enough hint about this precedence of operators and everything. So, that it gives multiplication higher priority than addition and unary minus higher prediction higher priority than any other operator that you have in the statement. So, this produces like this, that E producing E star E, then this E produces within bracket E, and then this E produces E plus E, then this E produces ID, this E produces ID, then this E is broken down into within bracket E, and then this E is broken down into E plus E, and then the first E gives rise to this unary minus E, and then this E gives me ID which is W, and then this E gives me ID which is V. Now, So, when this parse tree is being generated, so you know that this LR parsing strategy, so it will be doing reduction in the reverse order. So, we have to identify the which reduction will be done at the beginning. So, the first reduction that will be done is this one. Okay. The first reduction that is done is this one. So, E producing ID. So, this will be reduced. So, we number this reduction as 1 for the sake of our understanding. Then after that, the next reduction that will be done is this one, E producing ID. Then once these two reductions have been done, then this the number 3 reduction will be made, E plus E, and then after this reduction has been made, so this will be done. So, we number this as 4, okay, and after that, so this will be 5. So, this E producing ID, so this will be reduced next. So, this is E 5. So, you can what you can do is that you can start looking from the bottom left side, and then you try to see like how far can you proceed. Okay. So, when I start with the bottom left side, so I can see that I can do this thing, but I cannot do this. So, I after doing this I have to stop and go towards right a bit, and then see what is the next available reduction. So, that is this one. And then once these two are done, so this reduction is now ready. After once this is done, this reduction is now ready. So, but after that I find that I cannot proceed further. Then I have to come back and see what is the next operand at the next reduction at the lowest level that is possible. So, I find that this is the next reduction. So, so now this is 5, then after this is done. So, this is our number 6. So, this is 7, and once these are done, so this is 8, this is 9, this is 10, and this is 11. So, that is how so this so we call it annotation of parse tree. So, so there is something more, but we will come to that later. Now, what semantic action takes place when we look at different reduction steps. So, at reduction step number 1, that is this reduction. So, what we have to do is that we have to look for the corresponding rule. So, E producing ID, it says E dot place equal to ID dot place and E dot code equal to null. So, this E dot place equal to ID dot place. So, ID dot place is Y. So, E dot place equal to ID dot place. So, this is done, and the code is null. So, so it is not written here. Then the second reduction, E producing ID. So, this E dot place equal to Z. So, that is done, and then that is ID dot place. Then at reduction number 3. At reduction number 3, we have got E producing E plus E. So, let us go back and see what was the corresponding action. So, it will first generate a new temporary variable. It will first generate a new temporary variable in E dot place, and then it will generate the code E1 dot code, E2 dot code, and this particular line being generated separately. So, how is it happening? You see that this E dot place equal to T1. So, here I have got a new temporary variable T1, and then E dot code, E1 dot code and E2 dot code. So, they are null. Okay, E1 dot code, E2 dot code are null. So, nothing done, and then this new temporary, it says the E dot place, that is T1 equal to E1 dot place plus E2 dot place. So, Y plus Z. So, this is the code that is generated. So, the code that is generated T1 equal to Y plus Z. This line has been generated. After that, it will come to reduction number 4. So, within bracket E, and then within bracket E, the action, the semantic action is this E dot place equal to E1 dot place, E dot code equal to E1 dot code. So, that is what is done. So, E dot place equal to T1. So, E dot place equal to T1 and E dot code equal to this line only. Then at reduction number 5, so I have got this E dot place equal to W. There is no E dot code. Then at reduction number 6, so it is unary minus. So, this we did. So, if you look into the action for this unary minus, you see that it is so it is written like E producing minus of E1. So, that is a new temp will be generated, and E1 dot code followed by this temp generation of this extra thing. Okay. So, that will be done. So, that is done here. So, this T2, the new code that is generated. So, the new place has been generated at T2, and then T2 assigned as unary minus W. So, unary minus W, so that will make it this, they can make this minus W part. So, this way the code generation continues. We will go through this in the next class.